All right, I apparently posted the wrong video to yesterday, so I'm going to correct that. All right, today we're going to do chapter 16. I would say chapter 16 is probably the hardest chapter in the book, is my guess. If it's not the kinetics, it is going to be chapter 16. In chapter 16, we do our weak acid, weak base. So we have our Ka, Kb, calculate pHs. So we did some of that already, and that's not easy. Then we're going to get into common ion effect and buffers. And by far the hardest thing that we're going to do is the acid-base titration, which is everything that the whole chapter does all in one problem. All right, so we have our solutions of weak acids and bases. We did some of that already. Polyprotic acids, base ionizations, common ion buffers. So this is a very long chapter. As you see in the homework, there were very few questions in chapter 15. Chapter 15 is one of the easier chapters in the book, followed by chapter 16, which is acid and base, but it is the more difficult acid and base things that we're going to do. All right, and so that's why there is almost all the homework out of chapter 16. The test is going to be acid-base. Almost all of the questions are coming from chapter 16. All right, so we have a monoprotic acid. So a monoprotic acid means it has one acidic hydrogen. So anytime I have a weak acid that is monoprotic, I am always going to write HA. I don't care what the A part is, if it's the acetate, if it's whatever it is, if it's the fluorine. When it's HF, it's not that much easier to write. I might just write HF. But some of these have very long formulas for the acid, and it doesn't matter what the whole formula is, so you can just write HA. And so your HA reacts with the water. Water is a liquid to give H3O plus and A minus. All right, and so you have your conjugates, your HA and your A minus. You have your H2O and your H3O plus. Again, remember conjugate means differs by one H plus. Now, H3O plus, that is a strong acid. All right, it's not in a list of strong acids because all acids are neutral, and this one has a charge, but H3O plus is a strong acid. All right, and so on this side, you have a weak acid. All right, and so remember, your equilibrium always favors the weaker acid and base, and so the weaker acid and base are always on the same side. So this if HA is your acid, then of course H2O has to be your base. And since we know that HA is weaker than H3O plus, we know that this is also the weaker base. The weaker acid, weaker base are always on the same side. And so H3O plus is the stronger acid, A minus is the stronger base. All right, so you have your equilibrium always favors the weaker acid and weaker base for every reaction that is a weak acid ionization. That is always going to be your reactant. So when you have your concentration of products, which is how you're going to find the equilibrium constant over concentration of reactants, and it always favors the weaker acid, weaker base, which are always your reactants. That means you're going to have a lot of reactants and very few products, which means that all Ka values are going to be small. I'm going to show you a list of Ka values. Every one of them has an exponent that is negative. All right, so again, your weak acids, they're going to label your weak acids, and in this case, they have it as acetic acid, and if you like to write C2H3O2, then you can write C2H3O2. I see that acetic acid is a weak acid, and I also know it's a monoprotic acid. notice that you have acetic acid. It has a total of 4 H's. Only one of them is an acidic hydrogen. Those are the ones that are written first. And so this is a monoprotic weak acid, which means one acidic hydrogen weak acid. So I'm still going to write this exactly the same way. Is I'm going to write this as HA, and I know that when I'm talking about acetic acid, that my A is my acetate. All right, and so it's just easier to write. You can just write it as your HA plus H2O, H3O plus, and your A minus. So that works for any monoprotic weak acid. All right, so you have your concentration of products over reactants. It's always going to be small. All right, now they're going to ask for degree of ionization. So we did a little bit of that yesterday, except yesterday I called it percent ionization, and it's exactly the same thing, except degree of ionization is the fraction. The percent ionization, you simply take that and multiply by 100. All right, so degree of ionization times 100 is equal to your percent ionization. Remember the equation for that. It is the X over your initial concentration. All right, so that's how you get degree of ionization. Times 100 will give you percent ionization. All right, and so here's another one that is a monoprotic acid, HC6H4NO2. If you like writing HC6H4NO2, knock yourself out. I see a monoprotic weak acid, so I just write it as HA, where my A is C6H4NO2 minus. I prefer to write the A. Also, when I write my Ka expressions, I usually don't add water. I go to H plus and A minus. Again, all acids are aqueous. All right, and so if I write that my Ka, that is the concentration of H plus, concentration of A minus, over my concentration of HA. If you add the water, which is fine, that's a liquid, it does not go into your equilibrium. And instead of writing H plus, we have H3O plus, but we know that H plus and H3O plus are exactly the same thing. All right, so we have a solution that is 0.012 molar of this weak acid. And so that is my initial. So we're going to do initial, change, and equilibrium. So the initial concentration is 0.012 molar. That's 0, that's 0. So you can't have zeros at equilibrium. So minus X plus X plus X, it has to go to form some. So at equilibrium, we have 0.012 minus X. We have X and we have X. And so we plug that into our Ka. So the Ka is the H plus, which is X, the A minus, which is also X, divided by the HA, which is the 0.012 minus X. All right, and so now we have that Ka is equal to X squared over 0.012 minus X. And now the question is, what is the Ka? So part one, what is Ka? So we have to find Ka. All right, so you're either going to have to find X or you're going to find Ka. In this case, we're going to find Ka. So X has to be given. So what else is given in the problem? Well, the pH is given in the problem. And so the pH is equal to the negative log of your concentration of H plus. And this H plus is at equilibrium. So your pH is equal to negative log of H plus. The H plus concentration is the H plus at equilibrium, which is X. And so now we just solve for the concentration of H plus. And so we have pH 3.39 is equal to the negative log of H plus. Now to solve this, you have to take the negative of both sides, and then you have to push your inverse log, second log button, which is on your calculator a 10 to the x. So this is 10 to the negative 3.39 is equal to the H plus concentration. All right, and so that is then equal to x. And so then you plug that in to x right here, you plug that in to x right there, and you have your answer. To get your degree of ionization, remember that is x divided by your initial. Now, the question asks for degree of ionization, so we don't multiply by 100. And so we simply take our 10 to the negative 3.39, whatever your calculator reads for that, divided by your initial, which is your 0.012. And that's your answer for degree of ionization. All right, so again, we have our initial, which is 0.01200. It has to go to the right. You can't have 0. And so minus x, and you have your equilibrium. Then we write out our Ka expression. Again, I wrote H plus, I wrote A minus, I wrote HA. Exactly the same thing, where your A is your anion. Your A minus is your anion. All right, so now you do the substitution, and we plugged it in. So we had this equation, and then we had to solve for x. We had to solve for x using the pH. So now you have your pH. So the pH is 3.39. Now to put this into your calculator, you have to take the negative of both sides, and then to get rid of the log, you have your anti-log, which is your 10 to the x button. Your second log button is your 10 to the x button. And when you push your 10 to the negative 3.39, your calculator reads 4.1 times 10 to the minus 4. So now you plug that in. So we had x squared over 0.012 minus x, that's Ka. Now we have x. And so you're going to plug in your 4.1 times 10 to the minus 4 and square it. Divide by your 0.012 minus 4.1 times 10 to the minus 4. And you just push the buttons on your calculator, and you have your answer for Ka. And that is 1.4 times 10 to the minus 5. And so your answer for Ka, when you put those numbers in, is 1.4 times 10 to the minus 5. All right, so Ka, we knew it was going to be a small number. Every Ka is a small number. Every Ka has a negative exponent. Right, so you can write it as 0.1, 2, 3, 4. All right, again, the negative exponent means that you have a lot of 0.000014. All right, so it's a small number, much less than 1. Every Ka is going to give you a number less than 1. All right, but then we had to take our x divided by our initial. All right, so again, the degree of ionization, you take your x value, 0.00041 divided by 0.012. You have your 0.034. Again, if you wanted it to be a percent, you simply multiply by 100, and now you have percent ionization at 3.4%. All right, so again, if you wanted the percent ionization, you simply have to take your degree of ionization and multiply by 100. All right, so I told you there would be a chart with the Ka values, and I also told you that they were all going to have negative exponents. And so here is a chart of Ka values, and they all have negative exponents. All right. Now, when you have a negative 10, a negative 7, negative 11, negative 10, negative 13, negative 8, those negatives, when you're doing successive approximations, you don't even have to check your first answer is your answer. When you have a -5, most likely your first answer is your final answer. The -4s, usually it takes 3 approximations, but it does depend on your initial concentrations. And the -2, you might want to do the quadratic with a number that is a -2 exponent. That is a relatively large Ka value. And so the Ka value also tells you how acidic your acid is. So when we look at your carbonic acid, which is a diprotic acid because it has 2 acidic hydrogens, all right, so you can take off the first H as a Ka1, so we would call this one the Ka1, and then you can take off your second hydrogen, which we would call our Ka2. And so these are conjugates. All right, so they differ in 1H plus. Your H2CO3 to your HCO3 minus, they are conjugates, differing by 1H plus. Of course, we know that the one that has the one more H is the acid, and the one that has one less H is the base. All right, and so we can see that Ka1 will always have a larger Ka value than your Ka2. All right, and so always your Ka1 will be larger than Ka2. When we go to the next one and look at phosphoric acid, now we have a Ka1, which is definitely the largest of these acids. Of course, the H3PO4 is the strongest acid with the largest Ka value. And then Ka2 is in the middle, and then Ka3 is the smallest number, 10 to the minus 13. All right, and so the weakest acid here is your HPO4 minus 2 with the smallest Ka value. And so you need to relate the Ka value to the acid strength. So the larger the Ka value, all right, and so when you do the Ka, remember that is your H plus concentration, A minus concentration over HA. All right, so if you have a large Ka value, that means you're going to have a larger amount of H plus, which means you're going to be more acidic. If you have a very small Ka, you're going to have a very small amount of H plus, and you're going to have a weaker acid. All right, so there's going to be a lot of calculations with Ka. So you're going to be given the value of Ka in many problems and the initial concentration. And then you'll be asked to calculate the equilibrium concentrations of everything. All right, and then also with that, normally they will then ask for the pH. Because once you have the concentration of H plus, you take the negative log of that, and then you have your pH. All right, and so given the value of Ka initial concentration, all right, so the same thing again. So down here, you're going to calculate the degree of ionization and the percent ionization. That should have been up there as well. Remember, the only difference is the degree of ionization. When you multiply that by 100, you then have the percent ionization. They mean the same thing, just percent means you multiplied it by 100. All right, and then the last one here is what we just did. We were given the pH and we were also given the initial concentration. So then we had to find the value of Ka and the percent ionization. All right, so we did an example of that one. They said, here's your 0.0012, here's your pH, 3.39. Calculate Ka and percent ionization. All right, so there'll be problems like that as well. All right, so you can be given a pH and a percent or degree of ionization. All right, so if you're given the pH and the percent or degree of ionization, then you can solve for all the other. All right, so these are the things that can be given to you. So you can be given the pH, percent or degree of ionization, initial concentration, Ka. All right, there's always going to be something there they're not going to give you that you're going to have to calculate. All right, and then of course, like we did in the first example, in order to get our H plus concentration, which is the same as our H3O plus concentration, we got that from the pH. So they can give you the pH, you can get the concentration of H+. They can give you the concentration of H+, and you can get the pH. Make sure you can use your calculator to go either way on those. All right, and so you're going to use what they give you, and then you're going to find the things that they are asking for. That is why this chapter is very difficult. All right, what are the concentrations of the acid, hydrogen ion, and the ion of 0.1 molar? All right, so we have 0.1 molar, and we have this acid. All right, I'm not going to write the C6H4NO2. I am going to write HA. This is a monoprotic, 1H. It is a weak acid because it's not one of the 6 that we have memorized as strong. All right, and then it's asking here, what is the pH? All right, so what is the pH of this solution? All right, so all we have is our HA. You can write plus water and get H3O plus. I write HA gives H plus and A minus. All right, and I know that my A is C6H4NO2, and I know my A minus is C6H4NO2 minus. I'm not going to write all those things. I'm just going to write it as generic. All right, and so then I do initial change equilibrium. Initial, 0.1, 0 and 0. Can't have zeros, so it must go to the right. Minus X, and plus X. And so we have our 0.10 minus X, we have X, and we have X. All right, and so we have X squared over 0.10 minus X is equal to the Ka. All right, so the Ka we just calculated in that problem. This is the same acid that we had in that last problem. And when we calculated that Ka, it was 1.4 times 10 to the minus 5. And so this is 1.4 times 10 to the minus 5. All right, so minus 5 is very small. We neglect the X, and you end up with X squared over 0.10 is equal to 1.4 times 10 to the minus 5. And your X1, when you multiply both sides by 0.1, take the square root, you get 1.2 times 10 to the minus 3. All right, and when you plug that back in, if you want to check that, X2 is exactly the same, 1.2 times 10 to the minus 3. That is your answer for X. All right, so now you always have to see what is X. So back up here, what is X? Well, X is your concentration of H+. All right, and so to find the pH, pH is equal to the negative log of 1.2 times 10 to the minus 3, and your pH is equal to 2.92. All right, so, and then to find the degree of ionization, you simply take your X divided by your initial. So the X value, 1.2 times 10 to the minus 3, your initial, 0.1. All right, and so that is a 0.012. That is your degree of ionization, which is what they asked for, or 1.2% if they ask for percent. So degree of ionization is the decimal. The percent, you multiply that by 100 to give the percent. All right, so they're going to work all that out for you again. You had your initial concentration. We didn't add anything else. They are zeros. And so it has to go to the right to form it. So at equilibrium, you have your 0.1 minus X, X, and X. You plug that into your Ka expression. All right, and then I think they're going to do it by, I'm not sure how they're going to do it. They're going to do it by the quadratic equation. All right, and so they are going to solve this by doing the quadratic equation. I will always use successive approximations. All right, so they put it into the form of ax squared plus bx plus c is equal to 0. All right, and then they plugged it into their quadratic equation, and they got the 0.0012, or the 1.2 times 10 to the minus 3. the same answer that you would get by doing the successive approximations. All right, so then you just plug in your numbers. All right, and so when you take your x value, which is the 0.0012, and you're calculating the concentration of your HA, well, your HA concentration was 0.1 minus x. And when you take your 0.10 minus 0.0012, you remain at 0.10. So 2 decimals minus 4 decimals, 2 decimals, you round that to 2 decimals, it's 0.10. And so your initial concentration and your final concentration of your weak acid did not change because the amount that went to the right was extremely small. Your H plus concentration and your A minus concentration were both the X value, 0.0012. And then the pH, you take the negative log of the 0.0012 and you do get the 2.92 pH. And then your degree, you take your X divided by your initial. Again, that's 0.012. And if you wanted the percent ionization, it would be a 1.2% for your ionization. All right, so here they're going to give you a simplifying assumption. So basically what they're going to say is if you do this and you take your initial concentration of A divided by your Ka and you get 100 or more, you do not have to put X in and check it. All right. So if your initial concentration divided by your equilibrium constant is 100 or more, then you have a less than 5% error, and then that is acceptable. And so the larger this number, then the less error you're going to have. So if it's equal to exactly 100, your error is basically 5%. If it's equal to 1,000,000, then your error is essentially 0. All right. And so so this is a quick way. If you take your initial concentration divided by Ka, if it is 100 or more, you are then allowed to keep your first approximation as your final answer. If it is not equal to 100 or more, then you either do the quadratic or you got to keep putting in your X value until you get the same answer twice. All right, so here is a problem. And your problem is with acetoacetic acid, which is the acid in aspirin. All right, so you have your acid. All right, again, you can write HC9H7O4 every time. Again, I will not. I'm going to write that as HA, monoprotic acid, 1 H out in front. There's 7 or more, but there's only one that's acidic, the one out in front. All right, and so my HA goes to H plus and A minus. And I'm looking for my initial concentration. So they didn't tell us the initial concentration. They said that the tablet contains 5 grains. All right, or 3.25 grams. Yes, that's what I want, 3.25 grams. So I have 3.25 grams of my acid. And so I have to divide by the molar mass. And so you got to add up 1 plus 9 times 12 plus 7 plus 16 times 4. And you get, I think, 180.2. That's right. All right, so you take your mass divided by your molar mass, and that's going to give you your moles. All right, and we want our initial concentration, so we have to divide that by liters. All right, and so they said that we are going to put that in 0.5 liters of water. All right, and so that 3 grams is not going to change that amount of volume enough to change the overall volume. So we have a 0.5 liters of solution. All right, then they give us the Ka, which is 3.3 times 10 to the minus 4. So when we do our calculations, all right, so we had our molar mass of 180. All right, so then we have our moles. When we divided that, we got our 0.00180 moles. And then we divided by our 0.5 liters. All right, so now we have our initial concentration. All right, so the concentration always in molarity. Now, to see if we can just do successive approximations and X1 is our answer, we take our initial concentration that we have now calculated, 0.0036, divided by the Ka that they gave us, 3.3 times 10 to the minus 4, and we get the number 11. And so the answer is no. This one must be solved by the quadratic. Well, or if you're doing successive approximations, it might take you 5, 6, 7 until you get the same answer twice. All right, and so this one, you cannot use the X1 as your answer. All right, so you'll have to check it and check it and check it. If it is 100 or more, then you can simply go with your X1 is your final answer. And that amount of error is going to be less than 5%, which is then an acceptable error. But in this case, you would have to do the quadratic or the successive approximations until you get the same answer twice. All right, so we set it all up. We have our initial 0.0036, 0 H plus, 0 A minus, has to go to the right. All right, and so we're going to end up with x squared over 0.0036 minus x, which is equal to our Ka, which is 3.3 times 10 to the minus 4. All right, so if you're going to do successive approximations, that is fine. It's going to take a lot of approximations. You get your x1, you plug it back in. You get your x2, you plug it back in. You get your x3 until you get the same answer twice. Or you do the quadratic equation. And so you have to put it into the form of, right here, your ax squared plus bx plus c is equal to 0, and then you plug in the negative b plus or minus the square root b squared minus 4ac all over 2a. All right, so in this case, you can still do successive approximations, but it's going to take a lot of them, or you plug it into your quadratic equation. And when you plug that into your quadratic equation, you get a 9.4 times 10 to the minus 4 for your x. All right, so that is equal to your H plus or H3O plus. That is also equal to your A minus. All right, and so if we want the pH of this, then we need to take the negative log of that. And so your pH is equal to the negative log of 9.4 times 10 to the minus 4. So that is 4, that is 10, which is almost 1. That's going to give you, let's see, what does that give you? 3.03. So 3.03 is your pH. Trying to do logs in my head, it is not easy to do. All right, so if we go back and calculate our CA for the first problem here, where we did the quadratic equation. All right, so in this problem, we had our Ca over Ka. So our initial concentration for this problem was 0.1. Our Ka was given as, or calculated from our previous example, 1.4 times 10 to the minus 5. So if you do that, you bring your minus 5 up, it's plus 5. Then the 0.1 times the plus 5 is 4, and then that's going to be a fraction. So this is something times 10 to the third. It doesn't matter. Once you know it is 10 to the third, now you know that that's greater than 100. So in this case, when I did the successive approximations, this tells us that X1 is the answer. So when you get your number, it's going to be in the thousands, some thousand. So greater than 100 is all I need to know. And so once I know it's greater than 100, when I take my initial concentration divided by my Ka, then I can do x1, neglect my plus or minus x, and then that is my final answer. That's within 5%, which is acceptable for the answer. All right, so you have prepared dilute solutions of equal molar, all the same concentrations. So every concentration is the same. We picked out acetic acid, we picked out nitrous acid, and hydrofluoric acid, and hydrocyanic acid. And we want to rank these from highest pH to lowest pH. All right, so we look up our Ka values. All right, so we find in our chart that HF has the Ka value 6.8 times 10 to the minus 4. All right, so that is the biggest number in this chart. All right, so 4.5 times 10 to the minus 4 is a little smaller. 1.7 times 10 to the minus 5 is smaller. And then 4.9 times 10 to the minus 10, a lot smaller. So very small. So this one is very small. And that means this is a very weak acid. So your concentration of products of reactants, that is your H plus. All right, so you have a very small concentration of H plus. All right, and so this is your very weak acid. So this is the weakest acid. All right, so they can then say this is going to have the highest pH. All right, so your weak acid has a high pH. This is going to be, write the word. So this one is going to be the highest pH. And HF, this is the largest Ka value. That is the strongest acid. Your strongest acid is going to have the lowest pH. So again, you have your cutoff. Your cutoff is 7. 7 is neutral. All right, so if you're going this way, you're acidic. If you're going this way, you're basic. So anything less than 7 is an acid. Anything greater than 7 is a base. Of course, the smaller the number you are, the stronger your acid. All right, and so if we want to go from highest pH to lowest pH, your highest pH is HCN, your lowest pH is HF. All right, so your highest pH is HCN, lowest pH is HF. So you just plug it in, put that in the order. So you need to know that the larger the Ka, the stronger the acid. The stronger the acid, the lower the pH. All right, so polyprotic acids. All right, so polyprotic means that we have more than one acidic hydrogen. All right, so a lot of these are diprotic, meaning 2 hydrogens. Phosphoric acid is triprotic. It has 3 acidic hydrogens. And as we showed in the list of your Ka values, that Ka1 is going to be larger than Ka2, is going to be larger than Ka3. All right, so let's do some calculations with vitamin C. So vitamin C, again, is H2C6H6O6. I'm not going to write all that. What I'm going to write is H2A. So now I have a diprotic acid. H2A is a diprotic acid. So in Ka1, I take off the first H. So I get H plus and I get HA minus. This is going to be Ka1, which is right there, 7.9 times 10 to the minus 5. For Ka2, I'm going to remove the second hydrogen. All right, so Ha minus is then H plus and A minus 2, and that's Ka2. And Ka1 is always larger than Ka2. 10 to the minus 5 is much larger than 10 to the minus 12. All right, so now I can do my calculations. When you do your calculations, you always do Ka1 first, then you do Ka2. All right, so I'm going to rewrite my Ka1, H2A, H plus, and HA minus. All right, initial change equilibrium. So I started with 0.10 molar. In the problem, it says 0.10 molar. All right, no H plus, no HA. It has to go to form it, minus X plus X plus X, 0.10 minus X, X, and X. All right, and so when I put in my X squared over 0.10 minus X, that's equal to Ka1, which is 7.9 times 10 to the minus 5. All right, so I want to neglect my X. I don't want to check it, so I'm going to validate my 5% rule. So if I take my initial concentration and divide by my Ka, I want to know what I get. My initial concentration is 0.1. My Ka is 7.9 times 10 to the minus 5. Again, I bring my minus 5 up. It is plus 5 times 0.1. That's 4 divided by 7.9. That's 3. All right, so again, I'm going to have a number about times 10 to the third. All right, so again, you can push the number buttons and get your answer. That is definitely greater than 100. So all I need to know is, yes, this is greater than 100. I don't need to know what the number is. And so what that means is I can neglect this X and I don't have to plug it back in. And so I simply multiply both sides by 0.1, and then I take the square root, and I get my X is equal to 2 point something times 10 to the minus 3. Answer, no. Let's go back. We got, that's what my X value for the first one. Square root that. All right, 0.0028. All right, so that is 2.8. I didn't know what the square root of 7.9 is. Yeah, it is 2.8. All right, so 2.8 times 10 to the minus 3. All right, so now I have all of those. So now I'm done with Ka1. Now I go to Ka2. So HA minus goes to H plus and A minus 2. All right, initial change equilibrium. Here is where you have to be careful. Your HA minus, well, that's X. That's 2.8 times 10 to the minus 3. H plus, note, that is also X. 2.8 times 10 to the minus 3. Your A minus 2 is 0. We didn't have any A minus 2 in Ka1. So the reaction has to go to the right. And so minus X and plus X and plus X. So at equilibrium, 2.8 times 10 to the minus 3 minus X, 2.8 times 10 to the minus 3 plus X, and X. So now we plug that into our Ka2. And so we have 2.8 times 10 to the minus 3. Now, and I'm going to neglect my plus X. I'm going to neglect my minus X times X, and 2.8 times 10 to the minus 3. So note, you're going to end up with your 2.8 times 10 to the minus 3 in both the numerator and denominator. And so that is going to cancel out. And your X value is simply equal to your Ka2, 1.6 times 10 to the minus 12. All right, so now we have everything we need to know. That X is your A minus 2. So your A minus 2 is 1.6 times 10 to the minus 12. And if you do it a million times, you will get the same answer. Your A minus 2 will always be Ka2. So if the question is, what is your concentration of your A minus 2, you simply look at Ka2 and that's your answer. 1.6 times 10 to the minus 12. That is always going to be the answer. You can work it out. You will get that answer. It's always going to be the answer. Your A minus 2 concentration is always equal to Ka2. All right, we look for the pH. Well, the 2.8 times 10 to the minus 3 plus 1.6 times 10 to the minus 12, that's an extremely small number. It doesn't change the value at all. All of your H plus comes from Ka1. And so your X value here, this is equal to your H plus. It is also equal to your HA minus. And so you want to take the pH. Well, the pH is equal to the negative log of the 2.8 times 10 to the minus 3, which is a 2.55, I think. I think that's going to be 2.55. All right. So your Ka1 gives you all of your H plus and your A minus. The Ka2 only gives you the concentration of A minus 2, and that's going to be always equal to your Ka2. All right, we will pick up here tomorrow. I'm going to check that pH. Make sure it was, 2.55 was the pH.